Have you ever stopped to wonder, what is now? It feels so real, so immediate. It's the moment you're reading this sentence. It's the instant your heart beats. But is this now a fundamental feature of the universe, or just a stubborn illusion created by our human minds? What if I told you that in the grand cosmic scheme of things, your now is just a tiny localized event, a fleeting frame in a film reel that stretches across billions of years and unimaginable distances? The universe doesn't share our sense of a universal present. It operates on a much grander, more perplexing schedule, one that challenges everything we think we know about the flow of time. Our everyday experience of time is a simple, straight line. Yesterday is gone, tomorrow is yet to come, and the present is all that truly exists. We remember the past, we anticipate the future, but we live in the now. This intuition is powerful. It governs our lives, our plans, our memories. Yet, modern physics invites us to question this deeply ingrained belief. Science suggests that the distinction between past, present, and future might not be as clear-cut as it seems. Our simple, linear perception of time might just be a convenient story we tell ourselves to make sense of a universe that is far stranger and more wonderful than we can easily comprehend. Time, it turns out, is not just a clock ticking on the wall. This very journey, from your personal now to the dawn of everything, is a cosmic detective story. We're going to travel back, not just by days or years, but by billions of years. We will venture to a time before stars, before galaxies, even before the atoms that make up your body. We are heading to the very first moment, the ultimate beginning, where the rules of reality were written. By exploring the origin of the universe, we can begin to understand the origin of time itself. The ticking of your watch and the expansion of the cosmos are connected. They are two sides of the same incredible story, a story that starts at a single, unimaginable point. So, let's step aboard our ship of the imagination. Our destination is the most extreme environment we can conceive of, the birth of the universe. We will peel back the layers of cosmic history, one epoch at a time. We will see how a universe of unimaginable simplicity and heat gave rise to the complexity and structure we see all around us today. This journey will challenge our senses and our intuition. It will force us to confront the limits of our knowledge, but in doing so, it will reveal the profound connection between our fleeting experience of a moment and the grand, unfolding saga of space-time. Are you ready? Let's go. Our journey back in time takes us to a moment roughly 13.8 billion years ago. Here, at the very beginning, the entire universe was compressed into a point of infinite density and temperature. This isn't a point in space, it was space itself. Every star, every galaxy, every planet, and every one of us was contained within this infinitesimal speck. Scientists call this a singularity. It's a concept that pushes our language and our imagination to their absolute limits. At this moment, which we label time zero, the story of our cosmos began. Before this, we cannot say what there was, because the very concept of before may not have existed. Time itself was born in this cosmic crucible. Imagine all the matter and energy in the observable universe, hundreds of billions of galaxies, each with hundreds of billions of stars, squeezed into a volume smaller than a single atom. The temperature would have been trillions upon trillions of degrees, a heat so immense that the fundamental forces of nature as we know them were unified into a single, primordial force. There were no atoms, no protons, no neutrons. The universe was a seething, undifferentiated soup of pure energy. This is the state from which everything we see today emerged. The Big Bang wasn't an explosion in space, it was the explosion of space, an expansion that started from this singular point and continues to this day. This initial state, this cosmic egg, contained all the ingredients for our universe. It held the potential for stars, planets, and life. The laws of physics that would later govern the formation of galaxies and the evolution of species were encoded within its fabric. To think that the grand tapestry of the cosmos, with its intricate patterns of dark matter and shining nebulae, all originated from such a simple, yet infinitely potent starting point is one of the most profound discoveries of science. It connects the largest structures in the universe to the smallest possible scale. The history of everything is the story of this singularity unfolding over billions of years. Understanding this origin point is the ultimate goal of cosmology. It's the genesis moment of the scientific creation story. While we have a powerful theory that describes the universe from a fraction of a second after the beginning, shrouded in mystery. What was the singularity really like? Was it truly a point of infinite density? Or does our maths simply break down when faced with such an extreme reality? Answering these questions requires us to push beyond our current understanding and seek a new kind of physics, one that can unite the world of the very large with the world of the very small. As we try to peer closer and closer to time zero, we hit a wall. It's not a physical wall, but a wall in our understanding. This barrier is known as the Planck epoch. It represents the first sliver of time after the Big Bang, lasting a mere 10 to the power of minus 43 seconds. That's a decimal point followed by 42 zeros and a 1. During this incredibly brief instant, the universe was so small, dense, and hot that the laws of physics as we currently know them simply ceased to make sense. Our two great theories of reality, general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which describes the bizarre world of particles, give conflicting and nonsensical answers. In this Planck epoch, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, are thought to have been merged into a single, unified superforce. Space-time itself was not the smooth fabric we imagine, but a chaotic, roiling quantum foam. The very notions of space and time become fuzzy and indistinct. You couldn't say for certain where something was, or even when it was. This is the realm where gravity, the force that shapes galaxies, becomes as strong as the forces that operate inside an atom. To describe it, we need a theory of quantum gravity, the holy grail of modern physics, which we have not yet found. This is why we cannot truly describe the moment of the singularity itself. The Planck epoch is the earliest moment in time that our current science can even begin to contemplate. Before that, we are blind. It's like trying to read a book where the first page is written in a language no one has ever seen. We can infer that the page exists, but its contents are a complete mystery. This is the frontier of human knowledge, where the known universe gives way to the great unknown. It is here that we must confront the most fundamental questions about existence itself. So, what came before the Big Bang? The question itself might be meaningless. If time began with the Big Bang, then asking what came before is like asking what is north of the North Pole. There is no before in a context where time does not exist. Some scientists speculate about other universes or cyclical models, where our Big Bang was just one event in an eternal series of cosmic bounces. However, these ideas are highly speculative. For now, the Planck epoch stands as a monumental barrier, a signpost at the edge of our understanding that says, beyond this point, our physics breaks down. Just after the Planck epoch, something extraordinary happened. In a fraction of a second, the universe underwent a period of mind-bogglingly rapid expansion. This event is called cosmic inflation. In an instant far shorter than the blink of an eye, the universe swelled from a size smaller than an atom to something larger than a galaxy. This wasn't a conventional expansion, like the debris from an explosion flying outwards. Instead, it was the very fabric of space itself that stretched at a rate faster than the speed of light. This incredible growth spurt set the stage for the universe we see today, solving some of the biggest puzzles in cosmology. Imagine a tiny wrinkled balloon being inflated to the size of the Earth in a split second. Any initial creases or bumps on its surface would be stretched out until the surface appeared almost perfectly flat. This is what inflation did to the universe. It took the chaotic, curved, and lumpy space-time of the earliest moments and stretched it out to be incredibly vast and geometrically flat. This flatness is something we can observe and measure today. The fact that our universe isn't wildly curved, either collapsing back on itself or expanding so fast that no structures could form, is a direct consequence of this inflationary period. This rapid stretching also explains why the universe looks so remarkably uniform on the largest scales. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, it has almost the exact same temperature in every direction we look. How could regions of the universe that are now billions of light years apart have reached the same temperature? Before inflation, these regions were incredibly close together, close enough to have mixed and reached a thermal equilibrium. Inflation then ripped them apart, stretching them to opposite ends of the observable universe while preserving that initial uniformity. It's like two drops of ink mixing in a tiny puddle just before the puddle is instantaneously stretched into a giant ocean. Cosmic inflation was a pivotal moment in the history of time. It was the event that took the microscopic, quantum weirdness of the early universe and magnified it to cosmic proportions. The tiny quantum fluctuations, the little jitters in energy and density that are always present at the smallest scales, were stretched out during inflation. These stretched-out fluctuations became the seeds for all future structures. The slightly denser regions became the gravitational centers around which gas would later gather to form the first stars and galaxies. The universe we inhabit, with its clusters of galaxies and vast empty voids, is a macroscopic picture of the quantum world. Without the theory of cosmic inflation, the universe presents us with some deep and honestly pretty troubling puzzles. One of the biggest is the horizon problem, which we touched upon earlier. Why is the temperature of the cosmic microwave background radiation so astonishingly uniform across the entire sky? Distant regions of the universe, which are now billions of light-years apart, could never have been in causal contact to exchange heat and even out their temperatures. Light simply hasn't had enough time in the 13.8 billion years of the universe's existence to travel from one side to the other. Inflation solves this beautifully by proposing that these regions were, in fact, in contact before they were violently flung apart. Another major puzzle is the flatness problem. According to Einstein's theory of general relativity, the geometry of space-time can be curved by matter and energy. The universe could be closed like a sphere, open like a saddle, or flat like a sheet of paper. Our observations show that the universe is incredibly close to being perfectly flat. For it to be so flat today, it must have been even more exquisitely flat near the beginning. Any tiny deviation from flatness at the start would have been magnified over billions of years. Inflation provides a natural explanation. The immense stretching of space would have smoothed out any initial curvature, just as inflating a balloon makes its surface appear flatter. Furthermore, inflation helps explain the absence of certain exotic relics that standard Big Bang models predict should exist. In the incredibly hot and dense early universe, theories suggest that very massive, stable particles like magnetic monopoles should have been created in abundance. Yet we have never detected a single one. Where did they all go? Inflation provides an answer. If these particles were created before or during the inflationary epoch, the subsequent exponential expansion of space would have diluted their density to almost nothing. The universe became so vast so quickly that the chances of finding one of these relics in our observable patch of the cosmos are practically zero. So, cosmic inflation is not just an add-on to the Big Bang theory, it is a crucial component that makes the rest of the theory work. It elegantly resolves these fundamental problems with a single, powerful mechanism. It connects the quantum fluctuations of the primordial universe to the large-scale structures we observe today, explaining how a smooth, uniform beginning could give rise to a lumpy cosmos filled with galaxies and galaxy clusters. Inflation was the bridge between the inscrutable physics of the Planck epoch and the more familiar, expanding universe that followed. It was the process that took the initial conditions and shaped them into the cosmos we know. As the inflationary period ended, the universe was still an incredibly hot, dense plasma, but it was now vast and expanding at a more sedate pace. The energy that had driven inflation was converted into a flood of particles and radiation reheating the cosmos to an extreme temperature. It was in this fiery aftermath that the universe began to take on a more recognizable structure. The unified superforce that existed during the Planck epoch fractured. One by one, the fundamental forces of nature we know today separated and went their own ways. First, gravity emerged as a distinct force beginning its long and patient work of shaping space-time. Following gravity's separation, the other forces began to emerge as the universe continued to cool. The strong nuclear force, the force that binds atomic nuclei together, broke away. Then, the weak nuclear force and the electromagnetic force parted company. Each of these phase transitions, much like water freezing into ice, released enormous amounts of energy and fundamentally changed the rules of the cosmos. Particles like quarks and electrons, which were previously massless and indistinguishable in the primordial soup, acquired their distinct properties and masses through their interaction with the Higgs field, which switched on during one of these transitions. The universe was starting to develop a personality. This cooling and separation of forces had a profound effect on the fabric of space-time. Gravity, now acting on its own, began to work on the tiny density fluctuations that had been amplified by inflation. the slightly denser regions of the universe started to exert a stronger gravitational pull than the slightly less dense regions. This was the beginning of a process that would take millions of years, the slow, inexorable gathering of matter. Gravity was patiently laying the groundwork for future cosmic structures. The smooth, uniform plasma was beginning to curdle, drawn together by the invisible hand of gravity into the seeds of what would one day become galaxies. At the same time, the universe was filled with a chaotic battle between matter and antimatter. For every particle like an electron, there was an antiparticle like a positron. When they met, they would annihilate each other in a flash of energy. For some reason, which is still a major mystery in physics, there was a tiny imbalance for every billion antimatter particles. There was 1,000,000,001 matter particles. After all the annihilations were over, that tiny remnant of matter was left over. Everything we see today, every star, every planet, and every living being is made from that leftover fraction. We are the survivors of a great cosmic war. As the universe expanded and cooled, something remarkable began to happen. Complexity increased. The universe evolved from a simple, hot, uniform soup into a complex, structured, and cooler cosmos. This progression from simplicity to complexity is intimately linked to our perception of time's direction. We experience time as moving forward, not backward. We remember the past, but not the future. This is known as the arrow of time. Why does time have a direction? The answer seems to lie in a concept from physics called entropy, which is a measure of disorder or randomness in a system. The universe began in a state of very low entropy and has been moving towards a state of higher entropy ever since. Think of an egg. It's a highly ordered, low entropy system. If you drop it, it shatters into a disordered, high entropy mess. You will never see the shattered pieces spontaneously reassemble into a whole egg. This is the second law of thermodynamics in action. In a closed system, entropy always increases. The universe as a whole acts like this. It started in the highly ordered, simple state of the Big Bang singularity. Ever since, as it has expanded, it has become more disordered. The forward direction of time, the arrow we perceive, is the direction of increasing entropy. We remember the past because it was a lower entropy state, and we move toward a future that is a higher entropy state. This increase in disorder might sound counterintuitive. After all, didn't the universe become more structured with galaxies and stars? But the overall entropy of the universe did increase. While gravity pulled matter together to form ordered structures like stars, this process released immense amounts of heat and radiation, which spread out into the vastness of space, increasing the total disorder of the cosmos, far more than the local ordering decreased it. The formation of a star is a small pocket of increasing order in a universe that is, on the whole, becoming vastly more random. Our arrow of time is painted on the canvas of this universal trend. A few 100,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and neutrons, forming the first stable atoms, mostly hydrogen and helium. This event, called recombination, made the universe transparent to light for the first time. The light that was released then is what we now observe as the cosmic microwave background. From these simple atoms, gravity continued its work. Over millions of years, it pulled vast clouds of gas together, compressing them until their cores ignited with nuclear fusion. The first stars were born, lighting up the cosmos and beginning the process of forging heavier elements, the raw materials for future planets and life. Everything about our experience of time, from our psychological perception of its flow to the biological processes of aging, is a direct consequence of this cosmic evolution. Our sense of a past is tied to the lower entropy states of the universe, and our future is the path towards higher entropy. The very act of forming a memory in your brain is a physical process that increases the total entropy of the universe. You are an intricate, highly ordered system, a temporary island of complexity in a cosmic ocean that is steadily becoming more disordered. You exist because the universe has not yet reached its final state of maximum entropy, or heat death. The atoms that make up your body, the planet you live on, and the star that warms your world were all forged in the hearts of earlier generations of stars. These stars, formed from the primordial hydrogen and helium, lived and died, exploding as supernovae and scattering heavier elements across the galaxy. These elements, carbon, oxygen, iron, are the building blocks of complexity. They are the ingredients for rocky planets and for life itself. This process, driven by gravity and governed by the laws of nuclear physics, is another step in the universe's journey from simple to complex, all while following the overarching rule of increasing entropy. Our existence is a beautiful, temporary byproduct of this cosmic law. When you look up at the night sky, you are not just looking out into space, you are looking back in time. The light from the nearest stars has taken years to reach you. The light from the Andromeda galaxy has been traveling for over 2 million years, and the light from the most distant galaxies we can see has traveled for over 13 billion years. We are seeing these objects as they were in the distant past. The telescope is a time machine. This simple fact dismantles our intuitive notion of a universal now. The universe is a mosaic of different thens, a vast historical record that we can read just by looking up. Our perception of time as a steady, forward-moving river is therefore a local and personal phenomenon, rooted in the thermodynamics of our environment and the biology of our brains. It arises from the fact that we live in a universe that had a beginning and is still unfolding. We are part of the process. We are not merely observers of the cosmic clock, we are built from its cogs and wheels. Our fleeting lives are a small but meaningful part of the universe's grand story of becoming. A story that began 13.8 billion years ago in a state of unimaginable simplicity, and has been growing more interesting ever since. Even with all we have discovered, the Book of Time has many unwritten chapters. The story is far from complete, and some of the biggest questions remain unanswered. Our current model of the Big Bang, powerful as it is, leads us to the edge of a cliff, the Planck epoch, and can take us no further. What lies beyond that wall? Is the idea of a multiverse, a cosmic landscape of countless other universes, each with its own Big Bang and perhaps its own laws of physics, a fantasy or a glimpse of a deeper reality? Perhaps our universe is just one bubble in an eternal, frothing sea of cosmic creation. Another tantalizing possibility is that of a cyclical universe. In this scenario, our Big Bang was not the ultimate beginning, but just one event in an endless series of expansions and contractions. Perhaps our universe will one day stop expanding, reverse course, and collapse back into a big crunch, a new singularity that would then rebound in another Big Bang, resetting the cosmic clock and starting the entire process all over again. These are not just philosophical musings, they are active areas of theoretical research, as physicists try to build models that could describe a time before our beginning or a fate after our end. These ongoing mysteries remind us that science is not a collection of facts, but a process of discovery. We are explorers on an infinite ocean, and every new shoreline we reach only reveals more ocean beyond. The quest to understand the origin of time is one of the most fundamental adventures of the human intellect. It pushes our technology to its limits, from particle accelerators probing the conditions of the early universe to space telescopes capturing its ancient light. It forces our minds to grapple with concepts of infinity and eternity, challenging the very foundations of our perception of reality. The journey from the Big Bang to our present moment is the ultimate story of origins. It connects the quantum fuzz of the first instant to the consciousness that allows us to ponder that instant. While we may never know all the answers, the pursuit itself is a noble and deeply human endeavor. It is a celebration of our curiosity, our ingenuity, and our relentless drive to understand our place in the cosmos. The cosmic clock is still ticking, the universe is still evolving, and the adventure of discovery continues. The story of time is our story, and we are just beginning to learn how to read it.